Good day, everyone. My name is David Williams, Executive Director of the International Association for Energy Economics. It gives me great pleasure to welcome you to today's webinar entitled Modeling Infrastructure Risk Under Future Climate Scenarios. We're grateful to our moderator, Jonathan Gillis, and our distinguished panelists for today's timely discussion. But first, a little bit about the International Association for Energy Economics. We are the largest association specializing in the field of energy economics and provide a forum for the exchange of ideas, experience, and issues among professionals interested in the field. The organization produces 2 professional journals, a newsletter, and holds conferences and virtual presentations, along with a host of other products and services that you can find at our website at www.iaee.org. If you're not already a member of the association, we welcome you to join. A few housekeeping matters in regard to today's webinar before I hand things over to our moderator. First, this webinar is being recorded for those that cannot participate in today's live event. If you have questions for our panelists, please click the Q&A button at the bottom of your Zoom window to type your question. We've allocated sufficient time at the end of this webinar to address your questions. And now I'd like to introduce you to our moderator, Dr. Jonathan Gillis, who is an energy policy and resilience analyst at the National Preparedness Analytics Center at Argonne National Laboratory. John, over to you.
David, thank you so much. It's a pleasure to meet everybody. I will back off from the doctor title quite yet, but I am glad to be joined by some doctors today to discuss our topic. I'm excited to talk to you today about modeling infrastructure risk under climate change scenarios. I'm joined by some esteemed colleagues, Mustafa Altanakar, who's a computational hydrologist, and Ian Hyde, who's an energy management professional, and we'll be joined shortly also by Brayton Smith, who's an economist here at Argonne National Laboratory. Before I bring up the slide deck, just give you a little context about the group that we're coming from. We're with the National Preparedness Analytics Center at Argonne National Laboratory, and our focus there is on modeling and assessing risks from natural hazards, intelligent adversary threats, et cetera, to infrastructure systems, to assets, and to communities. And we help sponsors make decisions in uncertainty in that space. So obviously, with that being our focus, climate impacts are increasingly important. And so we've been doing a lot of work recently to think about how we might assess infrastructure risk under climate uncertainty. And so that's what we'll be discussing today. Bring up a slide deck here and jump right in. So, let's see. So just a quick introduction to our agenda today. What we're going to start with is just discussing climate risk overall, talking about averages versus extremes, giving some context about some of the terms that we'll be using as we dive into this discussion. And then I'm going to turn the conversation over to my colleague Mustafa, who will be talking about some of the tropical cyclone simulation work that he's been leading and how we are applying that going forward. And then we'll finally bring everybody together to sort of sum up the conversation about how we can apply these models, what stakeholders might be interested, what types of analysis we can do, and then opportunities for the future as well. But I want to start just by contextualizing what we mean when we talk about climate change risks. Climate change introduces 2 broad risk categories. One is a change in the average conditions, and another is a change in the extreme conditions. So the average conditions are what we experience sort of year over year, and changes in those can change the way that infrastructure systems need to be designed. They can also change the way that we interact with our environment. A good example of this in action right now is seeing the longer and longer fire seasons in California, which are caused by persistent temperatures for longer, lower rainfall levels, et cetera. So these are average conditions, and there's a lot of work that can go into modeling these average conditions and what that means for communities. But there's another category that we're going to focus on a little bit more today, and that's extreme weather conditions. Extreme weather conditions are the deviations from the norm, like droughts, floods, hurricanes, large wildfires, and they're a little bit more difficult to understand and think about risk because there's limited data on them. They're more complex to model, and so climate change is exacerbating both extreme conditions and changing average conditions. And so We have to do work as we think about adaptation strategies. We have to do work in both areas. And today we'll focus a little bit more on extreme conditions. We also know that there's a variety of stakeholders making decisions at different levels. So in some sense, we have the infrastructure system level, and that's bulk power systems, oil and gas, shipping industry, groups like that. We also have installation-specific or campus-specific concerns, and those are two different resolutions. So we have to pay attention to two different resolutions, and then we also have to pay attention to two different horizons. So planning decisions might be considering 20, 30, 40-year time horizons for investment, for siting, and things like that. Whereas operational decisions are a little bit closer to real time. And so we want to think about ways that we can feed planning and action in both of those time horizons as well. One of the things that sits underneath and underpins pretty much all climate work is global climate models. So many people may already be familiar with global climate models. We'll do just a quick review just to get everybody on the same page. But GCMs are very complex computational models that are designed to simulate the Earth's climate. If you look at the visual on the right, it explains a little bit more how this is done. It is done by basically dividing the world up into a three-dimensional grid space. And then a lot of computational work goes into understanding the relationship between grid squares, both vertically and horizontally. As you can see from the third bullet there's a lot of concerns that go into these, and there's also a number of models, and they produce different results. So balancing different models, looking at different models and seeing what they can tell us, knowing that some models are better at certain processes than others is important. And the Intergovernmental Panel on Climate Change, the IPCC, which a lot of you are likely familiar with, has used both a simple average and then a weighted average approach to considering these models in past IPCC reports. So when we're talking about global climate models, we have to also be cognizant of which models we're talking about, and whether or not we're talking about the sort of weighted average or simple average approaches that the IPCC is taking, or a specific model. What those models help us do is to look at the way that climate changes over time based on different carbon dioxide concentrations in the atmosphere. And so what this is showing here on the left is these cases. They're called representative concentration pathways. We have some high cases like RCP 8.5. This is a very fossil fuel intensive case. Basically, it used to be referred to as business as usual. I think the IPCC is backing away from that term now, but it's a high fossil fuel consumption case. Whereas RCP 4.5 and 2.6 are cases in which we see some short-term escalation in fossil fuel consumption and then a drop as we shift into other resources. And as you can see on the right side, the CO2 emissions are correlated with the temperature change. And so under these scenarios, we get vastly different temperature scenarios. And so when we do, for example, climate looks, we want to usually consider at least two scenarios because it helps us think about different futures that might be possible. The last part of what Argonne is doing with this climate data is working on downscaling this data. So a lot of times when you get global climate model data, it comes in these larger grid squares, which cover a good portion of the United States. And so we need to downscale that data to be visible at the local level or useful at the local level. There's a couple of ways of doing that. Argonne's environmental sciences group has been working really hard on a dynamic downscaling model that has helped us to get to 12-kilometer resolution in North America. And they're now working on 4-kilometer resolution, which is really neighborhood scale. And so we're very excited about that work. It's also very helpful in informing some of the work that we do, because the closer we get to sort of neighborhood level climate data, the better our projections can be and the better our analysis can be. So downscaling is an important addition to this climate modeling process. We're excited to have that group inside of Argonne as well, and we're looking forward to leveraging their work going forward. So I want to hand over now to my colleague Mustafa as we pivot from just sort of a summary of thinking about climate modeling to particularly a focus on extreme events. So Mustafa, if you take us away, please.
Yes, I hope everybody hears me. John talked about the data and how it is downscaled. And now I'm going to talk about how the extreme events are created using this data. One of the things that we do is the event modeling, because the data gives you the average conditions. And we use some statistical or dynamic models, or sometimes hybrid models, with the past or future climate data to model different types of extreme events. That could be tropical cyclones, non-tropical cyclone, extreme rainfall, snowfall, winter, extreme temperatures, tornadoes, wildfires, droughts, etc. And of course, some of these, such as tropical cyclones, have also a connection to extreme wind, extreme precipitation, coastal flooding, inland flooding, etc. And the wildfires and drought, of course, are related to grid resiliency, hydropower generation, those kinds of things. So once we have generated those extreme events, we do some statistical modeling, and the final goal, ultimate goal, is to be able to provide tools that allow resilient design, risk and reliability studies, consequence analysis, and mitigation. Next, please. Almost invariably, in all those natural hazards, we have a general scientific approach. So we start with the data that John presented. So that could be past climate data, which can be measured or reanalyzed, which means simulated, or it can be downscaled future climate data, such as the one produced by Argonne. Now, we take this data, since this data corresponds to average conditions, we have to be able to extract extreme events from this data. And in order to be able to do that, we use statistical models, dynamic models, AI and machine learning, artificial intelligence and machine learning models, or some sort of hybrid modeling to be able to create a list of events for the selected time horizon. So that would form a database, the third column, which is the database of detected or generated extreme events. Next is to interface these events in the database with geospatial data layers and assets, etc., and create tools that would allow us to do some event analysis using statistical models, such as extreme event probabilities, and then also create maps with the help of a map server, and also provide consequence analysis tools such as loss of life, infrastructure damage, dollar losses or economical losses, indirect or direct. And of course, all these structure is tending towards the final products that end user needs. And those are the tools that you are seeing over there. So next, please. Yes. So for illustrating this methodology, we have chosen the tropical cyclones. The tropical cyclones are costly, one of the costliest weather disasters. From 1980 to 2019, US has experienced 246 weather disasters, and the total cost was $1.75 trillion. And there were 42 tropical cyclones, and which caused $927.5 billion in damages, and this corresponds approximately $22 billion per event. And it is tightly related to also electrical subsector, because these events generally cause power outages. For example, 2017 Hurricane Maria holds the record. 50% of Puerto Rico was without power. And Hurricane Irma is also the fourth among top 5 power losses in history, with 200 million in Conis and 15 million in the Caribbean islands. Now, those hurricanes do not only cause destructive winds, but they also cause storm surges, which lead to coastal flooding, and they also lead to extreme rainfall, and combined with coastal flooding, lead to riverine flooding events. Next, please. So those are the tips. Next, please. Those are the types of things that we would like to model, but the problem is that the tropical cyclones have a very complex structure with multi-scale and multi-physics phenomena. And some of the images, show you how complicated these natural phenomena can be. It is possible to simulate with the current technology those events. Unfortunately, those are very complicated models. At Argonne, we know how to do that. The problem is even on supercomputers, each simulation would take days to complete. And therefore, they are not usable for the purposes of such a study where we want to study risk. So what we have done is that we have adopted the so-called GTI, Genesis Track Intensity Model. Those are models that allow us to create synthetic hurricanes very, very quickly, and allows us to generate thousands of tropical cyclone tracks. Next, please. An example is given here to explain the GTI model. I'm not going to go into technical details, but the first thing to do is the Genesis model, which is called G. And we select, either using statistical models or dynamic models, a location in the ocean where a hurricane is likely to be generated based on the climate data. Now, once a hurricane is generated, now we have to track its evolution. And this is the second model, which is called the T-track model. And what we do is that we calculate successive waypoints at specified time interval, which can be hourly, 3 hours, 6 hours, based on our selection. And we track the path of the hurricane on the map. And at each point, at each waypoint, now what we have to do is we have to calculate the intensity, and we use some sort of a Carnot cycle analogy to calculate the intensity. Intensity meaning that the wind velocity and the pressure drop at the center of the cyclone. So by combining G, T, and I, we are able to use the downscale climate data to create events which are tropical cyclones. And note that, some of these hurricanes that are created at the genesis time may or may not survive to a full hurricane. If their velocity drops below a certain critical value, we are just going to eliminate and stop them. Next, please. In order to be able to test our approach, we started using a set of data, tropical cyclone tracks, that you see in the image on the right that have been already generated. And this data set contains 10 1,000-year simulations. So using the current data, they have created thousands of hurricane paths. And you see those for 1,000 year, selected 1,000 year, superposed on the map. And what we are going to do is use those tracks to calculate the wind speeds over the United States, and also calculate the total rainfall due to hurricane over the land. Next, please. And for that purpose, we created a 20 nautical mile grid. And here on the upper left corner, the lower one is that those points are colored by the state, and in the middle, you have them colored by the county, and if you look at in detail to be able to see the individual points, for example, on Florida, this is the type of grid we obtain. And as I have mentioned, the grid size is 20 nautical miles. Next, please. Without going into the details, we use some special set of equations that allows us to predict the wind field around a hurricane at any point, at any position. And so here, for example, we are looking at Gustav 2008 hurricane path and the wind speeds that we have created around the path represented by red points. So those are 6-hour interval red points. And the blue, different shades of blue represent the wind speeds. Darker blue, low wind speed, and going to green and yellow, higher wind speeds. And you will see here, one of the characteristics of the North Atlantic hurricanes being clearly depicted here is that there is a bias to the right of the path, and wind speeds are much greater on the right side of the path, as shown in the figure. But this is only one single hurricane. What we have done is that we have done 10,000 of hurricanes, which were artificially created using last 38 years of climate data. Next, please. So if we prepare a map of the maximum velocity registered at each grid point, this is the type of map we are going to get. And here in this image, actually, the velocities after landfall are colored based on the color scale that you see on the left, which is the extended Saffir-Simpson scale for hurricane wind speeds. So the category 5 being the darker red color, and the blues are not even hurricane categories. The lowest, yellow is the lowest hurricane category, category 1 hurricane. Next, please. Next. And looking at those, we can create maps of return periods for different return periods, the wind speeds. So in the top row, you see 20-year, 50-year, 100-year. And the lower row, you see 200-year, 500-year, and 1,000-year return periods. And the scales of the wind speed is given in each. Of course, as you go to darker red color, the wind speed increases. They are given in meters per second, but if you would like to convert it to miles per hour, you need to multiply it approximately by 2.24. Next, please. Similarly, we also do have equations that allows us to predict the rainfall around the hurricane. And that's what we have done for the entire grid. And then we did some statistical modeling to come up with 20-year, 50-year, 100-year, 200-year, 500-year, and 1,000-year values, rainfall values. And those are mapped just like the wind, as you have seen in the previous slide. Next, please. It is, of course, possible to, using this data, to plot the exceedance probability curves for rainfall or for wind for individual locations. What you see over here is the Miami-Dade, a point in Miami-Dade in Florida. And what it shows on the left, you do have the values for different return periods, and also what is the minimum, maximum, mean value, and the different quantiles of the rainfall and wind speeds that were achieved during this thousands of synthetic hurricane scenarios. And what we do is that we create plots, as you see on the right side. The top one is for the hurricane wind speeds, and the lower one is for the rainfall amount in inches. This is the total rainfall that was recorded during the passage of a synthetic hurricane. Next, please. And we have compared our data, since this was for the current climate scenario. We compared it with the existing data, and our results are the green and blue, the blue-green curves that you see over there, and they agree very well with the studies and the results obtained by other researchers. And this allows us to verify that our approach is correct. And of course, the ultimate goal now is to go and do the same thing using the future climate data rather than the current climate data. Next, please. So what do we get from these kinds of plots? Actually, these kinds of plots can be used for the purpose of guiding the design standards for future buildings, infrastructures, etc. Because we do have these curves, we can calculate what should be the design wind speed for a given level of protection. That could be, for example, 200-year, it could be 500-year selected wind. And then we know for that time horizon, what is the corresponding wind speed for which we need to design structures. But those curves are also extremely useful for other purposes, especially for risk and reliability analysis and for mitigation strategies. So on the left side, what you see is the wind speed in miles per hour, and this is the gust wind speed actually. And the horizontal axis is the return period axis. What I can do is that I can bring in a damage curve that you see on the left, and this one is for single family homes, one-story wood. And that allows me to convert the wind speed into probability of exceedance of damage states. And you can see that there are different damage states, blue as being the lowest damage state, and the red being the most severe damage state. And now you can draw a parallel from a point for a given wind speed, which corresponds to a certain return period, and find out what the probabilities are for different damage states. And in this way, the damage state can be now related to return period, and those types of curves are then used for the risk and reliability analysis of infrastructures. Next, please. We prepared, and if there is time and interest, we can show you a simple, very simple user interface, but we are working on developing it. So on the left side, what you see is the map that I had already shown you, and it shows you the rainfall due to hurricanes. And on the right, the middle image shows you the map for, well, I'm sorry, there is a mistake. We should have inverted it. Left is the rainfall, and the middle is the wind speed map. And then on the right, you see the probability plots that I had been showing you for different return periods, how much rainfall and how much wind speed we have. These plots can be used for various purposes. And we can, of course, interface those with the GIS data layers of assets. So we can lay on our different types of infrastructures, buildings on these maps, and calculate at each location of interest what is the corresponding probability plots, and then convert them also into dollar amounts, or calculate for a selected area the economic impact. And so those components are still to be added onto this very simple prototype interface but it shows in which direction this work is continuing. Next, please. And I think that was the last one. John, I turn it over to you.
Thank you so much, Mustafa. And we've got a couple of slides on drought coming up too. But at this point, now that Mustafa's really described the way that we can model physical processes, run thousands of simulations, and then use that to estimate probabilities and return periods, we want to pivot and think about other hazards that we can do this with as well. One of those of great interest right now, obviously, is wildfires. Our environmental sciences group at Argonne has done some terrific work using the climate modeling that they have done down at the 12-kilometer resolution to forecast changes in the Keach-Byram Drought Index, the KBDI. The KBDI is an index that's correlated with wildfire probability in burned area. So by forecasting changes in KBDI, we can think about forecasting changes in wildfire probability, and that's the work that they're doing right now. And as we do that, similarly, or in a similar way to what Mustafa just described, we can then look for intersections between infrastructure systems and these future forecasted wildfire areas, and think about whether or not we need to steal assets in those areas, if we need to move assets, and what planning considerations might be. Going to the next slide here. So this work has already been done a little bit by Anthony Westerling in some terrific work 2018 for California's 4th climate change assessment. You can see on the left, looks like axis there. That's the climate model that he's looking at in these graphs. And as I mentioned at the beginning, different climate models will give different results. So Westerling's work is fantastic. He does it for a number of different global climate models, and so it's definitely worth looking into. But you can see how, for example, just this climate model forecasts changes in wildfire burned area but between now and the end of the century. And then we can adapt that, and work has been done by, I believe it was Berkeley, to adapt those burned area plots to wildfire probability plots. So this is on the caladapt.org page. You can find that there. And each grid square there shows the probability that a wildfire would occur in that grid square within a decade. A given decade. So this is a decade selected, I believe, 2030 to 2040. And obviously, we can use the information like this to do risk assessment for existing assets to think about where fires may occur. We could also use it for informed decisions for siting new assets as well. And Argonne is now working to extend some of that work and to include a lot of the work that's been done in our environmental sciences group to look at other indices that are helpful in predicting wildfire probabilities and try to also get to a finer resolution as well. Mustafa, I'll turn it back over to you.
Yes, thank you. And in this context, actually, we wanted to also talk to you about a recent study we have started, and that is related to droughts, which of course is related to also wildfires. And drought and hydropower, as you know, probably from the recent events, are very much related. On the upper left, what you see is the drought map with the points representing the hydropower facilities. And you can see that especially in Midwest and also on the West, a lot of power stations, hydropower facilities are in regions of drought, different severity. And below that, what you see is some sort of a statistics of how much of capacity, current capacity, is already in the regions of extreme drought. And as you know, in California, several hydropower stations have already stopped working, producing hydroelectric genericity, which is not very good for the grid because they are the regulators of the frequency and the power on the grid. Now, what generally we do is that we have maps that you see on the upper left corner, but those maps are not actionable information because they don't tell you at the local level, at the end user level, what is going to happen as far as the drought events are concerned. So this study is going to study the severity, duration, and frequency of the curves. And the summary of this study is given in this illustration on the right. What we do is that we calculate different types of drought indices. We stack them up as a function of time, as you can see, and then we use machine learning and artificial intelligence programs to detect the beginning and end of individual drought events and their extent. And we plot different characteristics. What was the volume? What is the severity, etc., as a function of time to obtain time series of drought events for future horizons. Of course, these are related to stream discharges and La Nina, El Nino type general circulations, jet stream. And the idea is to arrive, next please. To arrive SDF severity, duration, and frequency curves that you see here for different return periods. And it shows you severity relationship between severity and duration for different return periods. And of course, we do have also marginal probabilities that you see on the right, which relate intensity probabilities and duration probabilities to different quantiles. So this is a new study, and of course, it will provide at the local level drought information as an actionable information. John, it is.
Safa, thank you again. And this is our last slide here in our technical portion, and it helps us to tie together some of the work that we've been talking about doing climate and weather simulation and into some of the infrastructure models that we have. And this is an important final step as we look at infrastructure systems, because as Mustafa mentioned, from these simulation studies, we get two things. We get the probability estimates because we have so many that we can infer probabilities and return periods. But we also get individual event simulations. And so for each one of those storm tracks, we can run those through an infrastructure model. One of the models that we have at Argonne is Headout. This is a model that estimates the impact to the electric system from hurricanes. It's used generally in near real time to help utilities and communities prepare. But we can also set that model up to accept, you know, at a certain point, thousands of storms and look at the infrastructure impacts of those. And so that would help us look at, for example, potentially probabilities of outages occurring in various areas as a result of these storms, et cetera. And so this is a direction that we want to work toward. It's a great, exciting opportunity to be able to pull together infrastructure system models and climate and weather event models to try to combine those into something that gives decision makers on the ground actionable information, both for planning horizons and then also for near-term horizons. But at this point, I want to pivot our conversation a little bit and bring in my colleagues, Ian and Brayton. Ian, as I mentioned before, is an emergency management professional with about 15 years of experience in the field. And Brayton is an energy economist. And this is a great time to talk about, now that we've talked through how we do this, how we use this analysis. And so Brayton and Ian are terrifically sort of positioned to be able to talk about applications that are available, opportunities in the future. So I'm going to close out this slide deck here, and we'll bring everybody back up. And I'll direct the first question here to Ian and just say, Ian, now that we've talked through how we model these climate scenarios and how we look at extreme events, what are some of the stakeholders that might be interested in this information, and how do you think that they would anticipate using it?
Yeah, John, thanks. And thanks, Mustafa, for explaining the science and really touching on a lot of these use cases. And I'll mention with this research, we very much had practical use cases in mind from the outset, and that helped shape the approaches that we took, the outputs that we're envisioning currently, and those that Mustafa laid out earlier that we plan for in the future. And you can think about those use cases both in a pre and a post-disaster context, as well as a current and a future climate context. And so I think that's important to understand. From a pre-disaster context, some of the stakeholders that we would envision benefiting from this information could include state, local, tribal, territorial governments, federal agencies, but in addition, thinking about private sector infrastructure operators and others that may have a stake in risk management activities. And some of those specific use cases, for example, the Disaster Mitigation Act of 2000 outlines criteria for state and local governments to implement state, local, regional, tribal, territorial hazard mitigation plans. Within those plans, they lay out mitigation priorities, but they also assess potential risks and consequences. And so if you take the hurricane outputs, for example, that Mustafa laid out, having both a sense of the annualized risk or the frequency and what type of damages may occur with that, but also looking at more extreme scenarios such as a 1% or a 100-year event or a 0.1% or a 1,000-year event is going to help you look at all of the potential range of consequences and perhaps identify those specific risk reduction priorities. The same premise applies to emergency operations planning for state, local, tribal, territorial governments, where they're laying out roles, responsibilities, but also a lot of the assumptions for various different events. And understanding what those potential consequences could be, depending on the characteristics of the event, helps to better coordinate, helps to better assess what resources are needed, and to identify what those strategies are for emergency response operations. Thinking about risk reduction and future use cases, Mustafa already mentioned this, but two very specific use cases we had in mind were around land use planning, zoning and building codes, and things like capital improvement planning and infrastructure investment. From a land use perspective, you put yourself put your hat on as a local official, and you're thinking about what building codes to adopt or what to do with your floodplain management standards, or what to include in your long-range comprehensive plan. Those decisions you're making today are gonna influence your risk profile for the next 25, 50, 75 years in terms of where housing is built, in terms of where parks are built, green infrastructure, et cetera. And so having a sense for, again, those annualized risks as well as those extreme risks and also how they're changing over time is going to help inform what policies are adopted, which ones make sense for your jurisdiction or your community. The same applies for infrastructure investment. Mustafa already touched on it, but what standards do you need to build your infrastructure to be reliable, to reduce potential impacts in the future? And so that touches on just some of the use cases that we had in mind that really informed this research, John.
Yeah, I appreciate it. And I know one of the use cases that we've been considering is trying to help communities plan, particularly for hurricane impacts. And part of that is thinking about how hurricane impacts might have longer term impacts. And these models allow us to take a first step toward estimating some of those. Brayton, I know you've done some thinking in that area as well for us, and I want to bring you into the discussion to ask how we could use models like this, for example, to look at the impact of extreme events on communities over time, and what sort of tools and resources we might need to continue to develop to do that.
Thanks, John. So there's really two kind of aspects of economic modeling that you need to take into account to look at these kinds of things, at least for static type of events. And so the first would be economic damages, which you can think of as just like disruptions to buildings and infrastructure. And then the second part would be actual economic impact, which would be impacts of changes in spending patterns and changes in output by specific industries that occur from specific events. And so for the first, basically you would need an understanding of what types of infrastructure and what types of property are in like a zone where a disruption zone. And this is something that like models like HAZUS have taken into account over time, but basically looking at a newer version or a revised estimates using some kind of dynamic econometric analysis, really looking at what the causes and the indicators of increased economic damage would be. So like things like wind speed coming from these types of models that Mustafa has been proposing really lead to increased economic damages. And then the second part of that in the economic impact analysis would be linking specific types of infrastructure to economic activity. So the most obvious example of this would be electric power. So linking specific industries that just cannot operate with electric power would operate at a reduced capacity if they did not have access to electric power, and then also extending that to other critical pieces of infrastructure that would have a direct impact on output from specific industries.
Thanks, Brayton. And I do want to also invite just folks on the call here. If you have questions for this group, please do feel free to drop those into the Q&A chat down below. I'm going to pivot our discussion just a little bit to talk about opportunities for the future. I know this is a first step and an exciting step toward a direction where we can model these risks a little bit more at greater detail and model them with more hazards, et cetera. But I want to talk about some of the directions that we might need to take this work. And Mustafa, I'll turn to you and ask, what are some of the ways that you think that we can improve some of these models and where you think we need to be moving going forward?
Yes, what we are doing at the moment is, of course, at the beginning of this research. What we'd like to do is to be able to extend this to other types of hazards. And we believe that especially the tools are very important in order to be able to bring this information down to the end user. And for that purpose, we should be able to prepare intuitive and easy to use tools that do not necessitate a high level of professionalism, but allows the local decision makers to use the products that we are generating to do their analysis for risk and reliability of their system in the local context.
And I know you talked a minute ago about some of the stakeholders that we might want to think about. Can we dive a little bit into detail about some of those specific stakeholders and what sort of information they might need on a more granular level?
Yeah, absolutely. So a few things, and I think that touches on where we go with the research. Again, for local jurisdictions and infrastructure operators in particular, understanding the annual likely wind speed that a jurisdiction can face, maximum possible wind speeds, are going to affect some design standards, some land use practices. And so that's very much targeted at those officials and those organizations making those types of decisions. I think where we're going with this too is so far we've touched on wind speed and rainfall rates, but getting a clear understanding also of what that means for flood risk is going to affect those very same stakeholders. Again, from a planning purpose, what kind of land use standards, floodplain management, otherwise. I'll also touch on one of the use cases we thought about is more in that post-disaster context. And by having the huge library of events with different tracks and different characteristics, we're able to quickly provide information to those responding to an incident that can help inform what types of resources do they need to deploy to reduce consequences, prevent loss of life in the short term, but also set those longer term recovery priorities as well for how they're going to rebuild and hopefully avoid those same damages in the future.
Wonderful. And we've got a great question from Joshua here asking about long duration hurricane simulation and how we define lower return period hazard levels that are changing. So Mustafa, this gets to some of the discussion that we had earlier about using current data to develop and validate these models, but also ultimately shifting toward using future forecast GCM data. So could you talk a little bit about how we shift from where we're at now to how we use some of that data going forward, and then what that means for changing probabilities?
Yes, thank you. That is a very interesting question. And what we have done for the moment is to analyze only hurricanes wind speeds that are due to hurricanes. But of course, we could extend this analysis to the base level wind speeds as well, because we do have the data at different levels of atmosphere, different pressure levels of atmosphere from the GCM models, and we can use those to calculate also a base level, that means the lower level wind speeds for any given area. And we have plans to do that, but we have not yet at the moment, because we were focusing on getting the hurricane speed winds calculated and of course generating the hurricanes. But what happens is that actually what you are talking about is the sort of base level winds, which gives you the center part of the distribution, and the hurricane type wind speeds that we have presented are the tail or the extreme events part. Now, the idea, of course, is that to do the analysis for the base level winds as well, and then combine this whole thing into one single probability distribution that extends from very low speeds to very extreme speeds.
And Mustafa, I'll add on just the work that we pointed to with our environmental sciences group and forecasting Keach Byram drought index. That's work that takes the future climate work, extends it to look at a specific metric, which is this Keach Byram drought index, and then we can use that to think about how those probabilities change with wildfire. So there's two components to this, and one of them is looking at the actual event probabilities, and then the second one is to think about how those are influencing infrastructure systems. Our environmental sciences group has been doing a lot with wildfire in that, and we're now bringing that into our side to think about how it impacts infrastructure systems. So we're in an exciting place where we have two groups that can really work together on that. Brayton, I'm going to bring the next question to you and then over to you, Ian. This is a great question from Haley about how we can adapt these models to think about human security needs instead of just industry needs. And I think that probably gets to some of the community impacts that you were talking about earlier. Her specific question is if we think about intersecting this with census block data to think about how this might impact people in those census blocks. I'm not sure if you have any initial thoughts on that, Brayton, and then Ian will go to you.
I mean, I guess the first part of that would be if people are required to be out of work because businesses are shut down for one, and then also if they're required to be out of work because of just personal loss. So if there's a lot of, housing loss or people that are affected by certain industries not being affected, I mean, those would be ways to tie where employment in certain occupations reside at maybe more the block level. And then also you just have things like inconvenience of traveling farther to accomplish errands that you would need to do. But on the other, that would have to be a pretty large scale devastation to make that impact really visible, I would think. But yeah, I would think mostly which industries are affected and who's unemployed by that, and then also obviously the personal costs associated with loss of property.
May I add something, John?
Of course.
Yes, there are approximately 11 million, more than 11 million census blocks in the United States. It may have changed now with the recent census, but that was 2010 census event. And there is a population data set which is available at the 3 arcsecond grid resolution, which is about 90 meters resolution, and that's Landscan USA, and it is being updated. And using this data, it is of course possible also to bring this wind speed or rainfall or inundation data to a level of census blocks. I'm not sure census block economical analysis may not be very, very productive because it is such a small area and which may or may not have any economical significance. But of course, from the point of view of population density and population counts, census blocks are an important entity, and definitely some of the analysis can be reduced to this level. The selected 20 nautical miles is a pretty good resolution. And of course, from there, we can convert the results into census block polygons and do the analysis at census block level.
Yeah, and John, I'll just add, I think what Mustafa just touched on there in terms of us taking a grid-based approach is really important because it gives us the flexibility to evaluate impacts of various different geographic extents pretty effectively. And when you think about what data might be available from the census, as well as things like parcel data or the Landscan data that was mentioned, you can start to tease out what were the potential impacts, or what were the storm characteristics in areas with high percentages of certain different population groups. That can help you to provide an equity lens. It can help you to look at who might be most vulnerable. So I think there are various different ways we can go about this, but building in that geographic flexibility with the grid-based approach was a starting point for enabling that kind of analysis.
Thank you, Ian. And we're coming up on time here. We've got two questions from Parfait and John that I'll touch on briefly. And then unfortunately, we can't go into too much detail on these. Parfait asks about whether climate models really adequately take into account, for example, tipping points. I think this is a complex question that probably is outside the scope of this conversation, but also a very important question. But it's one of the reasons why it's useful to think about using a number of different models. It's why the IPCC, I think, weights those. But obviously, Parfait, you point to some of the critiques about whether or not they do that appropriately, and I think that's there's reasonable debates to happen there. But as we go forward into this, it's helpful to think about the way that Westerling did his wildfire forecast, which was to use a number of different global climate models. And then it's a lot of effort to downscale each of those individually, and so there's just a lot of modeling and continued work that needs to be done in that area. But using multiple models can help us at least think about different scenarios, some of which may include concerns about tipping points more so than others. And then a last question from John related to how companies and infrastructure regulators think about using these tools and whether we're working with them now. We are working with some ISOs and with the New York Power Authority most recently, using some of this downscale global climate data to think about challenges that might be relevant in a particular region. We've done this in the past also with AT&T. So we are working with infrastructure owners. I think regulators increasingly are also leveraging this information, but this is an emerging field in a sense, and so it's important to just sort of highlight the value of it to investors who are making informed investment decisions, infrastructure owners who are citing that, and then also to regulators who can require, in some sense, or think about asking for analysis that's based on future climate scenarios as well. So thank you, everybody, for joining today. Thanks to my colleagues here for their incredible insights today. And thanks to David for giving us the opportunity to share today. It's been a pleasure. Do feel free to follow up if you have further questions. My email is jgillis@anl.gov, and I would be more than glad to continue the discussion. And David, I will turn it back to you.
Thank you, John. IAEE wishes to thank you all for really an enlightening discussion on how climate affects our weather patterns and all that detail. We are also living this right now. It's very, very obvious. So for those listeners, please be aware this has been recorded. We'll be live on our website later on today for you to listen if you've missed the live performance. Wish to thank you all once again for listening and remind you to check out IAEE at www.iaee.org. Thank you.